Welcome to another episode of the Part 145 EASA training from Phoenix Way Academy. Hi, I'm Sarah.
Hi, and I'm Sam.
Well, in this deep dive, we will continue our exploration of Part 145 EASA regulations, specifically Clause 145.A.48, Performance of Maintenance.
That's right. And this section 145.A.48, it's really fundamental for how maintenance actually gets done within an approved organization. It gets into the nitty-gritty, the practical side, making sure every single task isn't just finished, but done precisely. Ensuring safety and compliance.
Exactly. And for you listening, whether you're deeply experienced in aviation maintenance, maybe newer to the field, or just really curious about how aircraft safety is managed, understanding these core requirements is key. It's really where the practical application meets the rules for operational integrity. Okay, so let's unpack the core principles of 145.A.48. Where should we start?
Let's start right at the beginning with the very first point. Clause 145.A.48, subsection A. It sets a really critical foundation that says, the organization may only carry out maintenance on an aircraft or component for which it is approved when all the necessary facilities, equipment, tooling, material, maintenance data, and personnel are available. So, this isn't just a guideline, it's an absolute must. You simply cannot start a maintenance task if any one of these things is missing.
That makes complete sense. It's all about being ready, isn't it? Like, you can imagine a mechanic needing to do a complex engine check, but maybe the specific diagnostic software isn't working, or a unique tool they need is out for calibration. Or even a critical part is on back order. This rule stops the work before it starts in that kind of situation, preventing rush jobs or, worse, safety issues.
Precisely. It's a proactive safety measure. And building right on that readiness, subsection B of 145.A.48 deals with accountability. It clearly states, the organization shall be responsible for the maintenance that is performed within the scope of its approval. This means the organization itself is ultimately responsible. It's not just about the individual technician who did the work. It's a systemic responsibility for everything done under their approval. The buck really stops with the organization.
That's a really important distinction. So if, say, a part is installed incorrectly and it causes an incident later on, it's the approved maintenance organization that's held accountable, not just the technician. It really drives home why the organization's procedures, their training, their oversight, while that is so incredibly vital, it's a collective responsibility. Okay, so we have readiness and accountability established. Now, Clause 145.A.48, subsection C, brings in 5 critical endurers, things the organization must guarantee.
Yes, 5 key points. The first one, under subsection C, point 1, requires that. After the completion of the maintenance, a general verification is carried out to ensure that the aircraft or component is clear of all tools, equipment, and any extraneous parts or material, and that all access panels that were removed have been refitted.
Yeah.
This is fundamentally about housekeeping, you could say.
Mm-hmm.
Preventing foreign object debris, FOD, and making sure everything's put back together correctly. It's that final, essential check to make sure nothing's left behind. No tools, no rags, not even a stray fastener.
We've all heard those horror stories, haven't we? The forgotten wrench in an engine or a loose screw somewhere it shouldn't be. This simple verification, this final sweep, can genuinely prevent major failures, especially once the aircraft is flying again. It's a critical safety net.
Absolutely. Then, moving to subsection C, point 2, we get into something more proactive. An error capturing method is implemented after the performance of any critical maintenance task. Notice the wording, error capturing. This isn't just about finding mistakes later. It's about having specific methods built into the process to detect errors, especially on safety-critical tasks. It's like building in a safety check, specifically designed to catch potential slip-ups before they become a real problem.
That's fascinating. So it moves beyond just doing the task to actively looking for potential errors during or immediately after the task.
Exactly. And we'll definitely dig deeper into what counts as a critical task and these error capturing methods shortly. It's a really important concept. Next up, subsection C, point 3. Organizations must ensure the risk of errors during maintenance and the risk of errors being repeated in identical maintenance tasks are minimized. This tackles human factors head on. It's about having systems in place to prevent the same mistake from happening over and over, perhaps on similar components or systems. It pushes for systemic solutions.
Right, so not just relying on individuals to be perfect every time, but building processes to reduce that risk.
Precisely. Then, subsection C, point 4, focuses on data. Damage is assessed, and modifications and repairs are carried out using the data specified in point M.A.304 of Annex I, Part M, or point ML.A.3 304 of Annex VB, Part ML, as applicable. This just reinforces that you must use the approved, up-to-date technical data manuals, service bulletins, etc. for any repair or modification. No guesswork allowed.
Sticking to the book, essentially.
Absolutely. And finally, subsection C.5 requires ensuring the assessment of aircraft defects is carried out in accordance with point M.A.403B of Annex I, Part M, or ML.A.403B of Annex VB, Part ML, as applicable. This ensures defects are evaluated consistently and correctly according to the regulations, leading to proper classification and action.
Okay, so those 5 ensures in 145.A.48C really cover the whole post-maintenance phase, don't they? From the physical check for tools and panels to managing errors proactively, using the right data, and assessing defects properly, it's quite a comprehensive checklist.
It really is. It creates multiple layers of safety and quality control after the work itself is done.
All right, let's clarify some key terms now. The general material, or GM, often provides helpful context. What does it say for 145.A.48?
Yes, the GM gives us important definitions. First, for an authorized person, says this is a person formally authorized by the maintenance organization to perform or supervise a maintenance task. An authorized person is not necessarily certifying staff. That distinction is crucial. Being authorized by the organization for a task is different from being certifying staff with the regulatory privilege to sign a certificate of release to service.
So someone could be authorized to do a specific job and sign for that specific job internally, even if they aren't the ones signing the aircraft off to fly.
Exactly. It allows for delegation of specific tasks to competent individuals who might not hold full certification privileges. And that ties into the next definition of the GM, sign-off. This is defined as a statement issued by the authorized person which indicates that the task or group of tasks has been correctly performed. A sign-off relates to one step in the maintenance process and is therefore different to a certificate of release to service. So a sign-off is an internal verification. It marks a specific task, or maybe a few related tasks, as complete and correct. It's fundamentally different from the overall CRS.
Okay, so think of sign-offs as the internal checkpoints, right? Building blocks of assurance within the maintenance process itself. They track progress and accountability step by step before you even get to the final release. Makes sense. Now, you mentioned earlier the requirement for having everything available. The acceptable means of compliance, the AMC, gives some flexibility there.
Yes, AMC 14145.A.48A addresses that practical reality. It acknowledges situations where an organization might temporarily not hold all the necessary tools, equipment, material, maintenance, data, etc. for something in their scope. The key point is that the competent authority doesn't need to immediately pull the approval for that aircraft type or component if it's temporary. And if there's a solid commitment from the organization to reacquire tools, equipment, etc., before maintenance on the related aircraft or component may recommence.
Ah, okay. So if a specialized piece of test equipment breaks down unexpectedly, they don't lose their approval instantly. But, and this is the important part, they absolutely cannot do any maintenance that needs that specific tool until it's fixed or replaced and available again.
Basically, it allows for managing temporary issues, but the core principle remains. You need the resources before you start the work. No compromises on that.
Got it. Now let's shift gears slightly. The general material for subsection C mentions something called CDCCL. What's that about?
Yes, CDCCL, Critical Design Configuration Control Limitations, GM 14145.A.48 talks about these. These are basically critical safety features inherent in the aircraft's design, often related to fuel systems and wiring, that must not be compromised during maintenance. The guidance states, the organization should ensure that when performing maintenance, the CDCCL are not compromised. It particularly flags things like changes to aircraft wiring, even if seemingly unrelated to the fuel system. And interestingly, it stresses preventing issues by standardizing maintenance practices through training and not through periodic inspections.
So training is the key defense here, not just inspection.
Exactly. The idea is that technicians need a deep understanding, through specific training, of why these limitations exist and how to avoid inadvertently affecting them. You can't just rely on catching mistakes later.
Like incorrect wiring could potentially interfere with fuel gauging or even create an ignition risk near fuel tanks, right? Even if the wiring wasn't for the fuel system itself.
That's the concern. It requires specialized knowledge, which is why that dedicated training referenced in the appendices is so important. Maintaining the original design safety intent is paramount.
Okay, that makes sense. So CDCCL is about preserving critical design safety features through very specific practices learned via training. Now, let's get back to those error capturing methods and critical tasks we touched on earlier. This seems like a really core part of preventing mistakes. Covered in the AMC for 145.A.48C2, right?
Yes, absolutely central. AMC 14145.A.48C2 requires the organization to have a formal procedure. This procedure needs to identify the error capturing methods, the critical maintenance tasks, the training and the qualifications of staff applying error capturing methods, and how they ensure staff are familiar with all this. So it has to be a documented, systematic approach, no winging it.
Right. So what exactly is a critical maintenance task according to EASA? What kind of jobs fall into that category?
Good question. AMC 24145.A.48C2 defines these quite clearly. They are tasks that could directly impact flight safety. The examples given include 1. Tasks that may affect the control of the aircraft flight path and attitude, such as installation, rigging, and adjustments of flight controls. Also 2. Aircraft stability control systems, autopilot, fuel transfer. And 3. Tasks that may affect the propulsive force, including installation of aircraft engines, propellers, and rotors. And finally, 4. Overhaul, calibration, or rigging of engines, propellers, transmissions, and gearboxes. Basically things that make the plane fly straight, stay stable, and keep moving forward.
So really high consequence tasks.
Exactly. And the procedure should also describe how these tasks are identified, using various data sources like information from the design approval holder, accident reports, incident investigations, occurrence reporting, even feedback from training and audits. It's meant to be a data-driven process.
So things like rigging flight controls incorrectly or installing an engine improperly, those are prime examples. And they use a wide net to catch potential critical tasks, learning from past issues.
Precisely. It's about proactively identifying where the biggest risks lie based on design and experience.
Okay, so once you've identified these critical tasks, how do you actually capture potential errors? What are these methods?
AMC 34145.A.482 defines error capturing methods.
Hmm.
They're simply actions defined by the organization to detect maintenance errors that are made while performing maintenance. The key is that they are defined actions. They must be adequate for the specific task and how much the system was disturbed. Often it requires a combination of several actions, maybe a visual inspection, followed by an operational check or a functional test, or maybe a specific rigging check.
So it needs to fit the task, right? A quick look might be okay for something simple, but for landing gear, you'd want to see it actually retract and extend a functional test. And for flight controls, that rigging check is non-negotiable to ensure everything moves correctly.
Exactly. The method has to be robust enough to actually catch the kinds of errors that might occur with that specific task.
And one of the most robust methods mentioned is independent inspection. Let's explore that one.
Yes, AMC 44145.A.48C2 goes into detail on independent inspection. It's defined as an inspection performed by an independent qualified person of a task carried out by an authorized person. There are clear roles. The authorized person does the task, supervises it, and takes full responsibility. The independent qualified person performs the inspection afterwards and confirms it's satisfactory with no deficiencies found. Crucially, this independent person doesn't issue the CRS. Then the original authorized person issues the CRS or the task sign-off after the independent inspection is done satisfactorily.
And all this needs to be documented.
Yes, the work card system must record the identification of both persons and the details of the independent inspection. It's a formal, documented check by a second pair of qualified eyes. Now, regarding qualifications for that independent qualified person, the organization needs procedures to show they're trained and experienced in the specific inspection. This person could be, for example, certifying staff, support staff, or someone authorized for similar tasks who's had specific practical training. And interestingly, point B3 mentions even a commander holding a limited certification authorization. Having received adequate practical training could potentially perform one in certain contexts.
A commander. That is interesting. So independent really means qualified and trained for that specific inspection, not just any other person.
Correct. Competence is key. And how they perform it is also detailed. For control systems, for instance, the independent inspection should check correct assembly, locking, and sense of operation. This involves looking at disturbed parts, checking full movement, cable tension, correct operational sense, interactions between systems, and even software that is part of the critical maintenance task, checking version and compatibility. It's very thorough.
Wow, okay. So for flight controls, again, they're not just looking, they're checking the full range from the cockpit, feeling the tension, ensuring left means left, right means right, checking software. It's a deep verification.
It has to be, for critical tasks. Now, what happens in unforeseen cases? What if only one person is available? AMC 4.D addresses this with reinspection. This is where the authorized person performing the maintenance task is also acting as independent qualified person and performs the inspection. But, and this is critical, it should only be used in unforeseen circumstances when only one person is available. It can't be considered unforeseen if the organization just didn't plan properly for staffing. The CRS is issued after the task and the reinspection. And again, the work card needs to record all the details of the reinspection. It's a last resort, not standard practice.
That really underlines the commitment to having that second check, doesn't it? Reinspection is allowed, but only under very strict unforeseen conditions, and it still needs to be documented rigorously.
Exactly. It maintains a level of error capturing even in difficult situations.
So, to recap this vital part, identify critical tasks using data, implement appropriate error capturing methods like visual checks or functional tests, use independent inspections by qualified personnel as a robust method, and only use reinspection in truly unforeseen single-person scenarios.
That's a great summary. It's all about building layers of defense against error.
Okay, finally, let's bring it all together. How do procedures ensure errors are minimized overall and, crucially, not repeated? This is covered in AMC 145.A.48C.
Right. AMC 14145.A.48C3 outlines procedures aimed at two main things. First, minimizing errors and omissions generally. This means procedures should specify 1. That every maintenance task is signed off only after completion. Also, 2. How the grouping of tasks allows critical steps to be clearly identified. And 3. That work performed by personnel under supervision is checked and signed off by an authorized person. Basic good practice and accountability.
Standard checks and balances.
Yes. But the second part is specifically about preventing repeated errors. The procedures should ensure that no person is required to perform a maintenance task involving a removal installation or assembly-disassembly of several components of the same type fitted to more than one system on the same aircraft or component during a particular maintenance check. The idea is to avoid having the same person make the same mistake on, say, both engines or both landing gear legs during the same check, which could compromise redundant systems.
Ah, that's clever. So you deliberately break the chain to prevent one person's potential error from affecting multiple identical systems.
Exactly. Though again, it notes that in those unforeseen single-person situations, reinspection might be used. And GM 14145.A.48C3 reinforces this, suggesting organizations can implement procedures to plan the performance by different persons of the same task in different systems, or use those independent inspection or reinspection procedures.
So that twin engine example makes perfect sense. If you have critical work on both engines, best practice is to have different technicians do that same critical task on each engine. It's a really practical application of human factors principles to reduce risk.
It absolutely is. So what this all boils down to for you, the listener, is understanding this layered approach to safety. It's meticulous paperwork, yes, but it's also careful delegation, rigorous checks like independent inspections, and smart planning to minimize the chance of human error, especially repeated errors, as much as humanly possible.
It paints a picture of a highly structured, safety-focused system where performance isn't just about getting the job done, but getting it done right, safely, and accountably every single time. Our deep dive today into 145.A.48 has really shown us the incredible detail and foresight EASA puts into ensuring that aircraft maintenance is not just done, but done with the highest standards of safety, precision, and absolute accountability.
In the next deep dive, we will cover 145.A.50, Certification of Maintenance.
You've been listening to Phoenix Way Academy, where aviation knowledge takes flight. Until next time, keep your skills sharp and your standards high.